All right, roughly doing the next 10 questions or so, starting with number 12. Let's do it. We got this block on an inclined plane. This is going to get a little funny, so we're going to have to write some stuff down. Horizontal, vertical supports the plane, blah, blah, blah. We've got friction between the plane, and we want to know the force to pull it up with constant speed. So if we think about it, we got this force up, and fighting it, we got force of friction, and we've got F parallel component of gravity. It's got constant speed here, so they're equal and opposite. So basically our upslope force is equal or down. So up slope equals downslope forces. Upslope we got F, downslope we got, let's just say force of friction, remember is, we draw our little triangle. Remember this angle is the same as that angle. This is our perpendicular component, which is equal and opposite to normal force. And this is F parallel. So force of friction is mu Fn, which is the same as mu F perpendicular, which is going to be mu mg cos theta, if you look at this sucker. And in this case, we will say we've got 0.3, it's 5 kilograms, gravity's like 10 meters per second squared, but the cos is actually quite interesting. Remember, usually we go from angle to kind of like ratio of the sides, but right now we can just go straight for ratio of the sides. Adjacent over hypotenuse, like this is, I know it says 5 kilograms, so that's not necessarily the length of this, but this is a 3, 4, 5 triangle. It's a right angle triangle. So this is 5 meters as well. And so cos theta is just adjacent over hypotenuse, or 4 over 5, which works out pretty nicely. We can cancel out our 5, get rid of that. 10 times 0.3 is 3. 3 times 4 is 12. And then our F parallel, I guess I'll throw that over here, is just mg sine theta. And we can use the same kind of cute little trick. It's 5 kilograms times 10 times our ratio of the sides, which is opposite over hypotenuse, so 3 over 5. We can get rid of our 5 again, and 10 times 3 is just 30. So F equals F parallel plus force of friction, which is just 30 plus 12. And that's it, so 42. And we are done that guy. A little bit of a longer one. Let's try this sucker. We've got some function for position, which is great. We want to find out when net force would be equal to 0. So basically net force will equal 0 when acceleration equals 0 and no other time, because F net equals ma, and unless they've figured out a way to make a frictionless, or not a frictionless, a massless locomotive, it's going to be a that's going to 0. So really, let's just find out our function, our acceleration function, and figure out where that goes to 0. So we're going to need to take two derivatives, because dx dt is our velocity. So we take the derivative. Remember, our new coefficient is our old coefficient times the old exponent. So it would be 3t, and then our exponent goes down by 1, so it's now 2. And then we do the same thing for the 6t, so negative. Our new coefficient is our old coefficient times the old exponent. So 6 times 2 is 12, t, and then we got to subtract 1 from our exponent. So 2 minus 1 is 1. Usually you don't write it. And then you got plus 9t. T, that's really t to the 1. basically we're just going to get rid of the t. If that doesn't make sense, just think of it as 9t to the 1. Our new coefficient is our old coefficient times our old exponent, 9 times 1. This is 9. And then we do t to the old exponent minus 1. T to the 0, anything to the 0 is 1. So it's basically 9 times 1, which is just 9. And then we do the same thing. We got to take the derivative again to get our acceleration function. I'll do this a little bit faster. New coefficient is 3 times 2, which is 6. Subtract 1 from our exponent. We've got to the 1, so we can just leave it. And then this is minus 12t to the 1. So just like before, we got rid of the t. And then what happens to our 9? What happens to our 9 is that's really 9 times t to the 0. So our new exponent would be 9 times 0. Which means the whole thing's going to be 0. It goes away. Anyway, at this point, it's pretty easy to tell that, hey, what does t have to be for this to go to 0? And it would be 2. 6 times 2 minus 12 is 0. So t equals 2. All right, this next sucker. For 14, we want to know the acceleration of this block. We've got a rough surface with friction and all that stuff. It's going to accelerate along the surface. We're assuming it's not being lifted. So basically, it's big minus small. You know how like big minus small equals ma? Big minus small equals ma, where big is basically F cos phi, trying to haul it to the right. And then our small is this force of friction there. So we got F cos phi minus friction equals ma. Divide both sides by m, and we're done. That we solve for a. So this sucker, big minus small over m equals a. And then we want to find the coefficient of friction between the block and the surface. The coefficient of friction is basically friction. Let's go move this. I need some space. All right, we want coefficient of friction for this sucker. And coefficient of friction, force of friction equals mu Fn. In this case, Fn is, if you think about just the vertical components, we've got F sine phi, we've got our Fn, the ground pushing up on it, and we've got mg. So these got to cancel because it's not accelerating up or down. It's not flying up into the air, crashing through the earth. So it's not too hard to find Fn if up equals down. Basically, it's just Fn equals mg minus F sine phi. And then once we got that sucker, it's just basically plugging it in. Keep in mind we called force of friction F. So if we solve for a coefficient of friction, we got F equals mu mg minus F sine phi. And then if we just divide this by both sides, we're done. F divided by mg minus F sine phi. And if we look for that, we will likely find it. F divided by mg minus. Mg minus F sine phi. Oops, almost circled the wrong one. Silly me. All right, next guy is a little tricky. You don't have the math to solve this yet and won't until the end of the year next year if you take calculus, which you should if you're taking basically anything, but particularly if you're taking AP Physics, it's a co-requisite. So We can solve it though using what's called boundary values. Since we know we're talking about terminal velocity, so initially its velocity is going to be 0 because we're dropping this thing. It's released from rest, not thrown down. And if there is air resistance, things always reach what's called a terminal velocity, a point where they don't speed up anymore. So at time t equals infinity, it's going this terminal velocity. If you wait long enough, it's going this terminal velocity. So basically, we're going to look at what the velocity is when t equals 0, and look at what the velocity when t equals infinity and see if it matches up. We can figure out what the terminal velocity will be by saying we want our terminal velocity will occur when your acceleration is 0, because then it's not changing anymore, hence the terminal velocity. Terminal velocity is going to keep going like that. It's not going to change. And so basically G has got to equal BV if that's going to be 0. So if G equals BV, your terminal velocity, your velocity where this happens, is just G over B. And we just got to check all these options and see that it's 0 when at t equals 0, because you're just releasing it, and it's G over B after t is infinity. So if we look at this sucker, if V naught is not 0, that can't be true because we released it, and it also doesn't. If t equals infinity, V is infinity, so this doesn't work either. For either your initial condition where it's got to be 0, or where your t equals infinity condition where your V has to be G over B. This guy again, if you set t to infinity, V would be infinity. Infinity times a constant divided by another constant is still infinity. So yeah, not that sucker, not that sucker. If you look at this guy, this would actually go to negative infinity because infinity squared beats infinity. So you're minusing infinity squared. So yeah, it's not that guy. It works for the initial case though. At t equals 0, it would be 0. If we look at this guy, if t equals 0, e to the 0 is just 1. Anything to the 0th power is 1. So it would start out with the velocity of g over b. But we want when t equals infinity for it to be g over b. So really, we're at our solution already, but let's just double check that it fits our boundary conditions. It's got to start when time t equals 0 at 0 velocity, and it's got to end up when t equals infinity at g over b, which this totally does. Notice it's basically this 1 minus e to the minus bt times g over b. So if this is 0 when t equals 0 and 1 when t is infinity, we're good. And if you check this out, if t equals 0, anything to the 0th power is just 1. You'd have 1 minus 1, so at time t equals 0, it would be 0, because this whole term would be, this whole term right here would just be 0. And then if t equals infinity, and sorry for the stop here, I ran out of space on my computer. Too many videos. Anyway, so what I was getting at is when t equals infinity, anything to the power of negative infinity is just 0. You're basically doing, or anything that is true if the number is greater than 1. If the number is greater than 1, anything to the power of negative infinity will be 0, because you basically got 1 over that thing that is greater than 1 to the power of infinity. That's going to get bigger and bigger and bigger and go to infinity. 1 over infinity is 0. So you got 1 minus 0 then, which is just 1. 1 times g over b. So it works for the final boundary condition. All right, and then we got this sucker right here. 3 blocks, 3 mm, and M are connected to strings A, B, and C as shown. It's pulled along a rough surface by a force of magnitude F exerted by string C. Coefficient of friction between each block and the surface is the same. Which string must be strongest in order not to break? Hopefully you just say C. If it doesn't make sense, if you think about it, A has to be strong enough to pull the friction force generated by 3M. Whereas B not only has to be strong enough to pull the friction force due to this 2M, it also has to pull this 3M. And then C has to be able to pull all of them. So it has to pull the coefficient of friction times 6M. B has to pull coefficient of friction times 5M, and A has to pull coefficient of friction times 3M. Oh, and all of that times G as well. All right, that's that sucker. So C has to be the strongest. And the previous one was that sucker. All right, last three we'll do in this video. So we've got a block of mass 3 kilograms initially at rest, pulled along a frictionless horizontal surface. So it's frictionless with a force shown as a function of time by the graph above. What's the acceleration of the block at t equals 2? At t equals 2, we can just basically read the graph. We've got 4 newtons pushing on it. If 4 newtons are pushing on it and it's 3 kilograms, it's just 4 over 3. So our F net is 4 kilograms at that point. It is 3 kilograms. A equals F net over M, 4 newtons over 3 kilograms. So it's just 4 over 3. And this next sucker, we want to know the speed of the block at 2 seconds. Now there's a couple ways you can do this. You can do kind of an area under the graph thing. You know how kind of area under the graph is equivalent to this guy times that guy, and if you go into like momentum and force stuff, you can just be like, hey, M delta V equals F net times T, if you remember that. Well, if your F net is varying, you can just do the area under the graph. So if we find the area under the graph here, it's equal to M delta V, and we can just divide by M. Area under the graph, we've got basically 4 times 2 divided by 2 to find the area of this triangle. So our F net is our F net is 4 times 2 divided by 2. So that would give us 4, 3, and then delta T, or delta V. So our delta V is just 4 over 3 again. And that gives us that guy. Area under the graph is F net times T. Another way to do it is we can just use average force to find average acceleration. So on average, it went from 0 to 4 newtons. So on average, it was going 2 newtons. So if we do 2 newtons divided by 3 kilograms, on average, it's accelerating at 2 over 3 meters per second. AAV is 2 newtons over 3 kilograms. 2 newtons on average between 0 and 4. And then we just multiply that for 2 seconds. We'd be like VF equals VI plus AT. VI was just 0 initially at rest. And then acceleration times time. So we got 2/3 times 2. And again, we get 4/3. So either way you want to do it. And last one for this particular video. We want to know the tension in the horizontal cord. And we're again using sort of like like our equilibrium unit. If this is 300, that means this is 300, because this is the only down force, and the upward component of this angled wire is the only upward component, so only downward, gravity down, and only upward is the upward component of the tension. Since it's a 45-degree angle, and that is like isosceles, yeah, whatever. Anyway, these side lengths are the same. So if this is 300 newtons, then this is also 300 newtons. And this is the only rightward force, so it's got to be equal to the only leftward force. And we're done with that guy. Thanks for listening. Sorry for the long video.